Hello, everyone. My name is Ivelin Georgiev. I'm a PhD student at Stockholm University and would like to present to you the second paper within my thesis. The topic of this talk, and hence the paper, is relating the Kinetic Sunyaev-Zel'dovich Effect and the 21 centimeter signal from the epoch of reionization. So, what is the epoch of reionization? Well, it's a global phase transition which occurs within the first billion years of the existence of the universe, where we go from a universe which is small, neutral, and cold to one which is larger, hot, and ionized. And we can choose to view this through the perspective of the neutral medium in terms of the 21 centimeter signal. A neutral hydrogen atom, which consists of a proton and electron, can emit a 21 centimeter photon. And as it travels from the line of sight to us, due to cosmological redshift, it will arrive in the radio range. So the hope to study the 21 centimeter signal from the epoch of reionization gives us an opportunity to see how the neutral medium becomes transparent to ionizing photons and then capture some of this information. So it's also giving us information about the state of the IGM. It's telling us something about the first stars and galaxies. And because of this, on different scales, it can tell us about cosmology and astrophysics. But we want to understand how this relates to other probes of the epoch of reionization. And in this case, the patchy kinetic Sunyaev-Zel'dovich effect, which comes from CMB measurements, is particularly interesting. Now, kinetic Sunyaev-Zel'dovich effect comes when photons travel CMB photons travel along the line of sight and interact with ionized bubbles, which have inside a bulk motion, so free electrons, which have occurred due to the ionization. So the ionization topology is imprinted at small scale anisotropies. And there has already been detections in this in RICHART 2021, and we have a sort of measurement, which is already telling us at least some initial constraints about the duration of reionization. And it's important to say that while the 21 centimeter power spectrum and signal is a probe of the neutral medium, the PKZ is telling us something about the ionized medium. And this is an integrated probe. So it's integrated along the line of sight, so the information is coded differently. Or moreover, each of these probes, the 21 centimeter power spectrum or the PKZ, will always be sensitive to the systematics of their instrument, but maybe studying them together will help us understand reionization as a whole better and avoid some of this. Now, in the first paper of my thesis, which I've put here, I looked at the decomposition of the 21 centimeter power spectrum. And then while doing this, I sort of recomposed and studied it again and arrived at the following expression. And essentially what you can get from this is that we find a relation between the 21 centimeter power spectrum, which is probing the neutral medium, as you can see here. These are ionized bubbles, which we don't see anything inside because they're ionized, and the electron density autocorrelation power spectrum, which is sampling the free electrons within these bubbles. So we're sort of getting a bridge between the two with these additional components. The power spectrum of the density field, the ionization fraction, and some more complicated terms like a cross-correlation between the density field and ionization field, or this one here. So much like the first paper, one of our interests was to try to understand if we can ignore these correlation terms and still retain the true 21 centimeter power spectrum. And the power spectrum, its amplitude is shown here for a fixed K scale, which is in Fourier space, so it's a length scale, real space. Here we see how the 21 centimeter power spectrum in our simulation truly evolves as a dashed line. And we can find that the expression in its full form, seen in orange, evolves exactly correct, so we can match it. But then if we remove one of these terms, for example, the one in green, so only this part, it doesn't quite match the same shape. You can see there's a dip, the power spectrum increases and then goes down. So when we only use this form, we sort of bias our model. But what we saw that we found quite interesting was that throughout reionization, as you can see here, how it's evolving from an ionization fraction of 0 to 1, using the simplest form without the cross-correlation, we can retain the shape of the true power spectrum, but we're biased, and we're biased more or less consistently. So this sort of urged our first paper, which is this work, where we actually use this for an analytic formula to bridge our two probes and we create a forecast where we use this model to generate the power spectrum. And because it is a forecast, this is the power spectrum that we fit next to. Now I say this, but how do we do it? Well, we want to get to the 21 centimeter power spectrum. And luckily for us, the density field is very well described and can be generated using CAM, or we can also use the parametric fits used in Planck analysis to generate the ionization history. And in fact, this asymmetric fit, which we use in our paper, uses the middle point of free ionization and the end point as input parameters to generate the ionization history and also produce the Thomson optical depth. So we have these two, which is nice. We ignored these terms for the time being. And with PE, we use the following model. This is a fit, which essentially depends on two parameters. One, which is sort of sensitive to the typical size of ionizing regions during reionization, and the other, which is sensitive to the amplitude of the electron density autocorrelation power spectrum. So we have a 4-parameter model, and this is what we will sample in our forecast to generate P21. We construct our P21, which will be our truth, using the simplest model, and we assign uncertainties to our data. We calculate analytically, given our detection of the 21 centimeter power spectrum, we calculate the thermal noise that the observation would have, as well as uncertainty due to cosmic variance. We also take the currently existing data point of the PKZ power spectrum, the patchy Kinetic Sunyaev-Zel'dovich Effect, and assume slightly smaller error bars than the ones currently present. We then sample our parameter space using CosmoMC for these parameters. We construct the reionization history using Zn and ZRE, the mid and end point of reionization, construct tau, and use both of these to construct PE, and we construct the density field from CAM. Then we can reconstruct the 21 centimeter power spectrum and the PKZ, and we perform a chi-square analysis and extract the best fit values. So the point is that we try to see if we can actually recover our original findings, and within the papers, you can see we study very different combinations of data points. For the case I want to show you, we particularly only assume early stage observations of the 21 centimeter power spectrum, assuming that there would be few, either with SKAO or another radio telescope like LOFAR or MWA. For this example that you will see, we assume that after 1,000 hours of integration time, we produce two observations of the 21 centimeter power spectrum at a redshift of 6.5 and 7.8 at this given K scale. This was motivated by some of the MWA upper limits and only one data point of the PKZ at L3000 when 10% uncertainty. And of course, as I said, in the rest of the paper, we study different versions, and you can see that this analysis eventually constrains the parameter space seen in blue. And these are our original priors, as you can see. So we get tight constraints on the endpoint and the midpoint of reionization, and we can constrain the characteristic scales and the amplitude of the electron density power spectrum. But it's very intuitive and interesting to also use the forecast to try to understand which component does what. So here in pink, you see we essentially turn off our P21. So we're just fitting, using our forecast, the PKZ only. So you can see the data correlates as follows. The constraints are much looser, but they tell us how our data correlates with the observables. You can see the ZRE and Zn. We're learning something about the duration of reionization, but we cannot exactly constrain them. And it's the same here with these parameters. Well, when we turn off our data of the PKZ and only fit with the 21 centimeter data that we have, but no PKZ, we're sort of sensitive to the endpoint of reionization, but maybe less exactly to where the duration is. And here we constrain the parameter space differently. What's important then is when we look at both of them together, the data are complementary to each other, so it betters our inference of the parameters of reionization. And the nice thing is that we can use our method to try to calculate different types of noise that would be inherent for LOFAR, MWA, and SKA. So we can start initially to think, had there been observations, or if there are observations, how will they be capable of constraining our parameter space with the forecast, and to think about the various improvements that could be done, or which K-scales would be needed for these telescopes to better constrain the properties of reionization. But this, of course, is a very initial study, so you can take it with a grain of salt. And as I said, this was done with just two 21 centimeter data points and one PKZ data point. But naturally, when we detect the 21 centimeter power spectrum, we should be able to have a lot more data. So here's an example. Notice the significantly smaller ranges of the priors. We have zoomed in of 4 data points of the 21 centimeter power spectrum and the same 1 data point of the PKZ. So now we are sampling the parameter space significantly better, and we've managed to constrain our parameters quite well, as you can see here. Oh yes, what I should notice is that, as I said earlier on, in our analysis, we can actually generate the Thomson optical depth. So we can actually extend our analysis and not just do the PKZ and the 21 centimeter power spectrum. We can use prior knowledge of the Thomson optical depth. So these are just different examples of studies we've done in the paper. Feel free to have a look. But essentially, you can see that we can, had they been bigger, we can already start applying some sort of prior based on the Thomson optical depth. Moreover, the higher order terms that I had crossed originally in the talk, we can think about a way to add them back into our analysis, so we can repackage them possibly as a cross correlation between the free electron field and the density field, or even perhaps the density field and the 21 centimeter field. So our forecast can also allow us to somehow include some sort of cross correlation data to build on and make a more unbiased estimate of the 21 centimeter power spectrum. This is all I wanted to say. Just to conclude, we've built a method to bridge observations of the 21 centimeter power spectrum to observations of the power spectrum of the patchy Kinetic Sunyaev-Zel'dovich effect, and we found that both data sets are complementary, and using both of them can help us better our inferences of the 21 centimeter power spectrum. Oh, sorry, the epoch of reionization, particularly the midpoint and the endpoint of reionization, the average sizes of ionized bubbles, and the amplitude of the free electron density power spectrum. I'm happy to take any questions, and thank you for listening.